Okay, so hope you all can hear me. So please confirm whether if it is correct. I mean, I'm properly audible or not in both chats. Okay, so let's begin the work related with the revision paper 5 from this point onwards. Okay. So, let's go for discussion. So, you can't stop. Okay, so on today's paper, I'll be starting the discussion with the essay section. Okay, and previously, some students ask me what to do with these structured essays things. Most of the time, I don't explain these structured essays within the class. So the point is this, okay? I mean, part of this session, part of this paper class is to cover your practicals. By the way, that practicals, I mean, we will be going for practicals only after we are ready with the MCQs and the essays. So for now, what I have to ask you is that you all can cover your practicals. Like if you are joining my class, I have already provided the lesson wise practicals for you as video lessons, so you can cover them up that way. Or otherwise, somehow you may cover those practicals. Okay. By the way, in the end, like just maybe a couple of months before the exam, I'll be beginning another separate lesson to cover your topics. Okay, day by day, within 2 to 3 sessions, we will be covering all the practicals that you have in your syllabus. Okay, so for now, don't worry about your practicals that much. So we will continue with the other 2 types of questions. So that's it. So today I'll be beginning with the essay paper, and we will try to cover these 3 essays, and then we will move into the MCQ. Okay. So first essay. So the question is based on hydrostatics and some circular motion principles. So hope you all can hear me, right? Okay. So the figure shows a hydraulic braking system which could be used to stop a rotating wheel. The force F is applied perpendicular to the brake pedal. The pedal rotates freely about a fixed axis through A and perpendicular to the plane of the paper as shown in the figure, and causes a force to be applied perpendicularly to the piston P1 of the master pump M. Okay. So the whole braking system is drawn there. So I'm just drawing what I want. There's the pedal, and this is rotating around this axis A. Okay, this is marked. I mean, this diagram is in already, and this is going to another piston which is connected to the master pump like this end, the master pump, and through the master pump, the braking liquid will be transferred. Like so, inside the master pump there is the braking liquid. So what does this piston do is this piston just away this liquid to this side. Okay, and then this is connected to another two pumps here. You can see them. Okay. So here, so let me complete the diagram quickly. Okay, so this is kind of a simplified version of the given diagram. Happens is, okay, what happens is, so here's the brake pedal. So by your foot, you apply some force on this brake pedal. So when you apply some force, so this is directly connected to this point A. I mean, this is rotatable. So this kind of try to rotate around point A. Then what happens is, uh, this is directly connected to this piston of master pump. So when this starts to rotate, this again will move this to this direction. I mean, this piston will be moved to this direction. So because of that motion of the piston, the liquid will be thrown to the this direction. I mean, thrown to the right towards the brake pads. Okay. Then the liquid is again flown to two other pistons. Okay. They call them, those are the secondary pistons. So at the end of the secondary piston, there is another, I mean, this is called secondary pump. Okay. So at the end of the secondary pump, there is another piston is connected to the brake pads. So these are the brake pads. Once I have drawn in black color, these are the brake pads. So what happens is when the liquid comes this way, I mean, the liquid again flows through this way, and it will again come through this way as well. So what happens is through the secondary pumps, these brake pads like pushed against the wheel. So this is the wheel. Okay. So just imagine the axis of the wheel is along the plane of the paper, axis of the wheel is along the plane of the paper. That means this is rotating like this. Okay, so the paper, I mean, if I draw the wheel, it will be just I mean, I can't draw the wheel on this board. එතකොට මේ wheel එක තියෙන්නේ අතරම මේ board එකේ plane එකකින් perpendicularly. يعني ඇතුළටයි එළියටයි. හරිද? So it is rotating along this axis. So what happens is once this brake pads push against the wheel, there will be friction forces developed. So because of those friction forces, the velocity of, or the angular velocity of the wheel will be reduced. That is what we call braking. Okay. So this whole process is explained given passage. So the resulting pressure is transmitted. The resulting pressure is transmitted by the brake fluid to the two identical pistons P2. So these are P2 pistons. Okay, this is M. And then the brake pads L attached to the pistons move a little distance and pressed against both sides of the rotating field. Assume that the brake fluid is incompressible. Cross-sectional area of the master pump piston T1 is 1 centimeter square. So the cross-section area of this is 1 centimeter square. And the cross-section area of secondary piston is 4 centimeters square. So there are two secondary pistons. So for one, the area is 4 centimeters square. Okay. This part, if F equal 10 Newton, so this person is applying 10 Newton force on the pedal. So this is the pedal. What is the force F1 applied on the piston P1 or required distance? The required distances are marked in the figure here. Okay. So what are the distance marked? You can see this distance they have marked 20 centimeter, and from the axis of rotation again to this point, we have marked the distance as 5 centimeters. Those are the two things marked. Okay, so asking to calculate the force F1 on this piston, that is this force. Okay, so what happens is when they apply the force on this pedal, so this will start motion. By the way, what will happen? So when it starts to motion, this will give a restriction. So there will be a tension force developed. Let's say F1. They have already called it F1. So because of this F1, this will feel a force. Okay. So how to calculate this F1 is, you can just consider the moment balance. Okay. Around point A, consider the moment balance. So you can do some simple assumption like that. Like when you apply this force, this is going to move with a constant angular acceleration, constant omega. That is constant angular velocity. So if the angular velocity is constant, no resultant moment. That means I can consider the moment balance. That means F into 20 should be here. There's another moment applied on this rod. Okay, being the moment balance for the field. Now so F into 20 should be equal to F1 into F5. F1 is equal to, here you can see these two get cancelled. F1 is equal to 4 times F, that is 40. Simple one. Then D. Calculate the pressure exerted on the by the master pump P1 on the brake fluid. Okay. So what is the pressure? So why a pressure is built up? This is not about the atmospheric pressure. Okay, atmospheric pressure is always there, so we don't have to worry about that. What is this external pressure? So that pressure is because of this force. You see, because of this force applied here, there will be forces exerted on this rod. That means there will be some force exerted on this piston. So because of this force, there will be a pressure. So you can calculate the pressure. We have called it P1. So pressure P1 is equal to Okay, so we will just assume it is P1. So pressure P1 is equal to force divided by area. And they have given, I mean, we already calculated this force, that is 40. So what is the area? So they have given in the passage that the area of the master pump is 1 centimeter square. So it is 1. By the way, it is in centimeter square. So centimeter square you can do to meter square by multiplying with 10 to the power minus 4. So your answer will be 4 into 10 to the power 5 Pascal. This should be your answer. Right? So if you find any questions, please let me know in the chat. Then part C, calculate the force exerted on the brake pads due to pressure exerted on the secondary pistons. P2. Okay. So what happens is, because of this F1 force, there will be a pressure building up on this brake fluid inside this master pump. Okay. Inside this capital M, there will be some pressure exerted due to this force. So what happens when you give some pressure to a liquid? So recall the Pascal's principle. So if you apply a certain pressure change to a certain point in the liquid, then that pressure change will be equally distributed to all these points in the liquid. So until the liquid remains continuous to all points, the pressure difference will be transferred. That means the same pressure you applied here will be exerted on P2 pistons as well, those secondary pistons as well. So they're asking to calculate the force, by the way. So how to calculate the force? So apply Pascal's principle. So this is by which we can relate the forces. So when you apply Pascal's principle, remember the theory, the pressure will be transferred equally. So initially the pressure was F1 over A1, it should be equal to here the pressure build up. Let's say the force acting on the surface is F2, okay. The force exerted is F2. What these? So what is the pressure build up? So if I assume the area to be A2, if the area is A2, the pressure is equal to F2 over A2. So you just can find F2 just by multiplying by A to the other. Just do the cross multiplication. Right? So when you do this, A2 they have given 4, F1 is we calculated 40, and this A1 is 1. So here see, just identify that I just substituted the cross section areas in centimeter square. So in this case, that's not a problem, because if I substitute in both places in centimeter square, those will be cancelled. Okay, so there it is not a problem. But here, when you're applying for A1, you always have to make it to meter square, because there's no one to cancel the units. There it is. By the way, here it is not. So 160 Newton. So this is the answer for the part C. Then D. Okay. So I already now calculated the force acting on these pistons here for the secondary pumps. Okay. So if the coefficient of dynamic friction between the brake pads and the wheel is 0.4, calculate the friction force acting on wheel due to each pad when they are pressed against the wheel. Okay. So let me draw it in another elevation. So here the diagram is on such that we see the wheel from this side. So when I am observing the wheel from this side, I just only see its thickness, right? So now what I'm going to do is I'm going to observe the wheel from this side. Okay, I'm assuming that I keep my eye from this side and observing the wheel. So what I should C is something like this. I'll see the wheel. So this is the axis of rotation. Now it is going out from the board, that is perpendicular to the board, and this wheel is rotating. So the brake pads are something like this connected here. Okay. Now they are pressing the wheel from both sides. Okay, so here you can see wheel is here, they are pressing against the wheel. So what happens is the wheel is trying to move, like the wheel is trying to rotate to this side. So when the wheel tries to rotate this side, because of the pressing, I mean these surfaces are obviously rough, huh? So being rough, and it is trying to like rotate to this side, so the friction forces will oppose it. So the friction forces will be developed like this. By the way, okay, note that this is the friction force acting on one side. I just give the friction force acting on this side, which I see. By the way, if I see the same scenario from the other side also, there will be another friction because there is also a brake pad. So that means there should be two such friction forces. So the total friction should be equal to 2 times F naught, 2 times F naught. So how to find F naught? So the dynamic case finding friction is like P naught. So friction is equal to mu times reaction. What is the reaction force here? Reaction force is the perpendicular force, right? So if you see from this elevation, from this side, what is the perpendicular force? It's nothing but this F2, isn't it? This F2 is the perpendicular force. So 0.4 into reaction is 160. So 64 Newton. So this is the friction force coming from a single side, right? You can see it. So let me write it somewhere else. Okay. So mu R is equal to 0.4. Reaction is 160. So 64 Newton. So the total friction should be 2 times that, that is 128 Newton. So this is the total friction acting on this wheel because of the brake pads. Okay. So I think you understood that section. So we can move to the next part 2. So I'll give you a few minutes to get notes. Okay. So meantime, if you have any questions, just raise them in the chat. Yes, right. So part 2. Before applying brakes, the wheel was rotating at freely at 600 revolutions per minute. Distance from the rotating axis of the wheel to the line of action, the friction force is 15 centimeter. Okay. The moment of inertia of the wheel about the axis of rotation is 0.1 kilogram meter square. Fine. Assume that the friction force remains constant through the motion. Okay. So part A. Calculate the initial angular velocity of the wheel in radians per second. So that's something easy, right? So they have given the data about angular velocity. How? They have mentioned like the initial rotating speed, 600 revolutions per minute. So I'll write it as RPM, revolutions per minute. So 600 revolutions per minute. So when you have given me this value, I always say in the class to convert this. So this is something about the frequency, right? So what do you mean by frequency? Angular frequency, you say number of rotations per second. Number of rotations per second. So this is rotations per minute. So how to calculate the frequency? So frequency is nothing but, so this is for a minute, for a sec. So 10 per second. So omega equal to 5f 2 times 3 times 10, that is 60 radians per second. So here, so you see, I took the value of phi as 3. That's because in the question they have mentioned. Otherwise, if this is not given, then you can't use it. You can't use like 5, 3.14 unless it is mentioned. Okay, so the initial angular is fine. Calculate the angular deceleration of the wheel. Angular deceleration, how to find the angular deceleration? So have they given a time to stop this? Right? I mean, in the next question, they are asking how long does it take to stop. So they haven't mentioned a time to stop. So you can't calculate with the angular velocity. So how can we find the deceleration? So alpha, the definition is this, but you can't go with that. By the way, there is another equation this alpha comes, that is the Newton's law, right? Tau equal I alpha. So can't you use this? So here in this first part, in this section, I have drawn you how these friction forces are there. So obviously, this angular deceleration is because of these friction forces. So what happens is, because of these friction forces, there will be some external torque developed. I mean, in the second part, they have also given this line of, I mean, the distance from the line of action is 15 centimeter as well. The friction force, the distance is 15 centimeters from the axis of the wheel. Calculate the torque. So it is moving clockwise. By the way, the friction forces comes to the other direction, that means anti-clockwise. So what will happen is opposing torque will be generated. So because of this torque, there will be a deceleration. So you can evaluate deceleration just by torque divided by the inertia. Value of inertia is also mentioned. So this is the formula. So first find the torque. Torque is equal to force times the distance. So the total force 128 Newton into the distance to the line of action is 15 centimeter, that is 0.15 meter, divided by the inertia point. Okay. So you can simplify this. When you do that, you should obtain like the answer will be, it is 64 and 192 radians per square second. This should be your answer. Okay. I think all clear up to this point. Then part C. How long does it take to stop the wall when the brakes are applied with F equal 10 Newton as above? So now we have done the conclusion. Okay, rest is easy. So now you already know the deceleration. Deceleration is 190 radians per per second. And the initial angular velocity also you calculated. Initial angular velocity is equal to, or let's say omega naught is equal to 60 radians per second. So how to evaluate the time taken to stop this ball, this wheel? Just use an motion equation for the circular motion. So what is the most appropriate circular motion equation? So we don't know the angular displacement, so exclude that theta. So the equation without theta is omega is equal to omega naught plus alpha theta. This is the same, right? V equal u plus at. Okay. By the way, this V equal u plus at is used for the linear motion, and the same thing for the system motion is this final omega is equal to initial omega plus alpha t. Finally, omega is 0. Initially, it was 60, and this 192. This is a deceleration. So for deceleration, when you apply it is in this equation, it is you should include a minus sign. Okay, that will give you the direction times t. So the time you can evaluate, it is equal to 60 divided by 192. So what is the answer? So you have to see, divide 60 by 192. No, for 60, 0, 60. So you put 0 point. For 600, it is 3. 3 into 2 is 6. This is 57. So 4 to 240 again, only 1 is there. Okay, only 1. Let's see. Yeah, just solving this by long division. 192 is 48. So 2. Okay, something like this. The answer, time is equal to 0.312 seconds. Fine. How far the wheel moves forward when it comes to rest? For this part, assume the radius of the wheel is 20 centimeters and rolls without slipping. Okay. Another easy question. So what they're asking is like, when you apply, this is something practical. Like when you if you have drive a vehicle, I mean even bike, when at the very moment you apply the brake, the vehicle will not stop. Obviously, it's because of the inertia. Okay, we talked about these in earlier lessons. Because this will move forward a certain distance. So now we are going to calculate it. So you see, at the very moment we apply the brakes, this will not stop. This will rotate. So how long does it take to stop? It will be 3 point, I mean, we initially found 0.312 seconds. So it will take that time to stop. So within that time, this will move some distance along the surface. I mean, if you remember, so they have given a very like important word, that is rolls without slipping. Rolls without slipping. So this has a like very important meaning. So if it is rolling without slipping, if it is rolling slipping, that means all the points on this wheel will be continuously touching a distinct point on the surface. So if the total angle rotated by this wheel is theta, I mean, this is the most important thing. If rolling without slipping, if the total angle rotated by the wheel is theta, and if the distance moved forward is s, then it should be equal to the radius of the wheel is theta. So if it is rolls without slipping, you can apply s equal r theta. That's So let's continue with the second question then. The second essay that is about surface tension again. Okay, so we had discussed, I think, couple of surface tension questions in this class right now, and that's kind of a very important part in the 10th lesson. Okay, define surface tension as always. It is firstly defining. So what do you mean by surface tension? I mean, you can do this by yourself. Surface tension is defined as the force per unit length. By the way, that's not enough. So you have to say like uh, the force acting perpendicular through the surface to a single side of an imaginary line drawn on a liquid surface with a unit length is called the surface tension. Okay, that means let's say this is a line which is drawn on a surface, liquid surface. So if the length of the line is L, and if the total perpendicular force on this line is F, then the surface tension is defined as force per unit length. That is, you have to define F by L. Okay, so that's the definition. Then V, soap bubble with different sizes are released into air by a device. Write down an expression for the excess pressure inside a soap bubble in terms of the surface tension of the liquid gamma, that's capital gamma, and the radius of the soap bubble. Okay, so the expression for the excess pressure is delta P is equal to 4 times the surface tension. Normally we use capital T. By the way, here they have mentioned gamma, so we have to go with that. 4 gamma over simple R. So this is the expression. Then a soap bubble of radius R1 combined with another radius R2 and a soap bubble of radius R0 is produced without any change of temperature. Okay. So there is the first bubble with radius R1, the second bubble with radius R2. It combined forms a single bubble with radius R0. Take the atmospheric pressure as capital P. So the pressure outside is capital P. Okay. The pressure outside is capital P. And the surface tension is gamma. So gamma is the surface tension, as they mentioned. The universal gas constant is R. So normally we use capital R for universal gas constant. First part. Write down expressions for pressure inside bubbles P1 and P2 in terms of P, gamma, Rn and R2. So the pressure inside two bubbles. So the one with radius R1, the pressure, let's say P1. For the next one, we can say the pressure is P2. So I mean, the equation is for the pressure difference. Obviously, we know the pressure inside is the highest pressure. I mean, compared to the external pressure, the pressure inside is high. So when you're taking the pressure difference, you should subtract from the higher pressure, that is the pressure inside. So P1 minus P, so if you apply the equation for the first bubble, P1 minus P, the excess pressure should be equal to 4 times gamma time divided by radius R1. So P1 should be equal to P plus 4 gamma over R1. So the same way you can do for the second bubble as well. So no need to do it again. I mean, start from the first equation. Just you can write same way, P2 should be equal to, same way P2 should be equal to P plus 4 gamma over R2. Done. R2 is absolute temperature of the sample is capital T. So here capital T is used for the absolute temperature, right? That means all these things happening constant temperature, which is capital T. Write an expression for the total number of moles of gas inside the combined bubble, that is they have used a simple MT. total moles in terms of P1, P2, R1, R2, capital R and capital T. Okay. So how do you obtain? So they have again given a hint. Use the ideal gas equation. There is an equation like this. Okay? For a given gas sample, if this is a gas sample, if the pressure inside is P, if the volume of the gas is V, and if the number of moles of gas, the quantity of gas is simple N, measured in moles, is simple N, and if the temperature is T, then pressure times volume is equal to N times R times T. This is a relation. So you can calculate the number of moles just by subjecting. Okay. By the way, the total number of moles you have to calculate in terms of P1 and P2. P1 and P2 are two separate pressures for two different samples. That means you have to calculate this total number of moles by taking separately. Let's say the number of moles in the first bubble as N1 and the number of moles in the second bubble and N2. Then the total number of moles should be equal to the sum of it. Okay, you can evaluate just considering the whole sample because pressures are two different pressures as well as the volumes are also two different volumes. By the way, when you consider separately, you can apply the equation. So for each sample, the number of moles should be equal to its pressure, its volume divided by R times the temperature. So the pressure of the first one is P1. Okay. Then the volume, it's a bubble, right? That means a sphere. So volume is given by 4.35 R1 cube divided by capital R times temperature T plus for the second one, pressure P2 4.35 R2 cube divided by R times T. Hope you all get it. So now, simplification up to this level is enough. By the way, let me write another step because there is 3 here. That's kind of ugly. So I want to make it some arranged equation like this: 4p1 5 r1 cube divided by let's say 4 5 upon 3 rt. I can take the whole thing out. This whole thing is available for both these equations. So 4 5 upon 3 rt p1 r1 cube divided by plus p2 r2 cube. That's the total number of moles. Third part, write an expression for the total number of Nt in terms of P, gamma, R naught, R and T. Okay. So initially we got formula for total number of moles by considering two samples separately. Now we are asking another expression for the same thing, Nt, in terms of P, that is the atmospheric pressure, gamma, R naught. That's something important. So R naught, where to find R naught? R naught was the final volume, sorry, final radius of the final soap ball. That means to evaluate in terms of R naught, you have to consider this whole soap ball. Okay, the final soap ball. So let me take the pressure inside this ball as P dash because it's not given. We don't know the pressure inside. Obviously, when we mix these two up, these two are at two different pressures. So when you mix it, the final mixture will be at a different pressure. It should be, right? Because all two different pressures when you mix it up, that should be again a different pressure. Okay, so considering the final bubble, you can evaluate the pressure inside P dash. How? P dash should be equal to nothing but P dash should be equal to P plus 4 gamma over the final radius. The same thing we did in part 1. You remember? Here, when you apply the formula, again I can show this. Okay, so the total number of moles then equal, I mean here I'm considering the final bubble. So considering final bubble, okay, when I consider the final bubble, the total volume should be equal to, sorry, total number of moles should be equal to, here the pressure. So the pressure inside is P dash. Now I obtained the equation for the P dash, that is P plus 4 gamma over R naught. Volume 4.35 R naught cube, that's a sphere again, divided by the gas constant times the temperature. I mean, this is enough. This simplification is enough. Okay, now again, that is also proved. Then hence prove that. So see how arranged this essay is. The question is beautifully arranged. So they have guided you go for the final answer. Okay, that's the beauty in recent exams. Most of the time, you are properly guided through consecutive parts of the question to achieve the final answer. Okay, now what they ask is, hence prove that the surface tension gamma is equal to some uh, relationship is given. So let's try it. So how to go for that? Hence means you have to use the previous results you obtained. So what are the previous results before this fourth one? These two. Here you see, I mean, considering separately, I have obtained an expression for the total number of moles. And again, considering the final bubble also, I got an expression. So this is for the same amount of gas, because even when you mix this up, the volume means, I mean, the same amount of gas should be inside the final bubble, right? If this is some amount, if this is another amount, same amount, the sum of the amount should be here. So this NT should be the same. So just equate them. So let me take this relationship, first one, this as the second one. So if it is the same, then one should be equal to. So that is how you hence prove, okay, using the previous results. So 4 phi upon 3 RT T1 R1 cube plus T2 R2 cube should be equal to, again I can rearrange this when I write here, 4 phi upon 3 RT using T plus 4 gamma over R naught cube. You see, I just rearranged the same equation. Okay. Because why? Because when I rearrange, I can easily solve. Okay, now just two simple expressions in both sides. So I'm gonna expand it. P1 R1 cube plus P2 R2 cube should be equal to T R naught cube plus 4. Is something missing? T gamma R naught cube. By the way, you see, if you see the final result, there's no any P1 or P2 included in the equation. P1 and P2 is removed. So here, how to remove P1 and P2? So earliest results, earliest of the question, what we did was we initially obtained relationships for P1 and P2, right? P1 was P plus 4 gamma over R1. P2 was P plus 4 gamma over R2. So just substitute it and see the result. Okay. I can see the result. All India behind America's needs. Okay. See the results. Okay. Again, I'm rearranging. So you see, in some terms, so again, I have to expand this. Okay. So I'm going to do the whole thing in my mind, like this kind of like a big one. Can do a lot of things. Yours also, by the way, you have to make it. So you see, I first expand this, and you can find in certain terms there is a p. So I'm taking all the terms, including a p, to one side, and I'm taking the other terms to the other side. Okay, so taking a function phi, r1 cube plus r2 cube minus r0 cube is equal to the other side. You can see 4 gamma is always there. 4 gamma in the other term, 4 gamma, 4 gamma. So 4 gamma I'm taking out. So if I do that, I get r0 cube minus, sorry, here it is not cube, it's square. Because when you solve this, r0, 1 r0 will be cancelled when you multiply this. So r0 square, sorry, r0 square. And here also, if you do the same thing, 1 r2 will be cancelled. So let me write r1 first, r1 r2 square. Yes. Okay, so now I see the result. So gamma is equal to, I mean, if you see the answer, you can just see like these two expressions, they are the same things, by the way, with a negative sign. In the answer paper here, the expression, it includes a negative sign. So what you have to do is you have to multiply the both sides by negative. It does not make any difference. By the way, you have to prove the one given. So when you include this one, you can interchange the signs. So p r0 cube minus r1 cube minus r1 r2 cube. Expression එක පෙන්වන්න තියෙන එක බලලා කරන්න වැඩක් හරිද? පොඩ්ඩක් පැත්ත වෙනස්නේ. So I just multiplied with the negative sign. Here r1 squared plus r2 squared minus r0 squared. And there's a 4. So final answer is taken. So that's how you go for final expression. Okay. So hence prove that part is out. Taken out quickly. Okay, sorry. that part. See. Okay, first part. The soap bubble mentioned above is formed at one end of capillary tube as shown in the figure. Plot the graph to show the variation of pressure from A to D. Okay, so something like this. So there is a capillary tube and there is soap bubble in the end. This point is A. Yeah, portion is called B. Here and the top it is called C. And this whole length, and here it is D. We have given this whole length as L. We will see how that is useful. Okay, so with the variation pressure, right? We have to plot the variation of pressure. Okay, so this is pressure. So here it is starting from point A until D. So let's do that then. So let me divide the sections. From A to B, it's some distance. From B to C, there is some distance, and C to D also there is some distance. Yes. So obviously, let's say, I mean, the external environment, the pressure is the atmospheric pressure. So all these areas, pressure is atmospheric pressure. So what is directly exposed into, I mean, what of these A, B, C, D regions, which is directly exposed to the atmosphere, you can see that the region CD, the region CD from C to D is directly exposed to the atmosphere. That means the pressure inside is P0, the atmospheric pressure. So let me take the level of atmospheric pressure like this. So this is the level of atmospheric pressure. So from C to D, pressure should be the atmospheric. It does not change. Okay, that's fine. Then now I'm gonna sketch the pressure at AB. Okay, next I'm going to look at it. So what can you say? The pressure from A to B. Again, even if it is not atmosphere, right, from A to B, this is not directly exposed to the atmosphere because there is always it is closed. From this side there is the liquid column as well as the solid walls, and from the other side there is a a soap bubble. So even if that is not exposed to the atmosphere, this is an air region. So the chemistry students and in physics also we learn, in a gas, if a closed gas is there, the pressure at all points should be equal. Pressure at any point should be the same pressure. By the way, this is the pressure inside the soap bubble. So if you remember, the pressure difference across the soap bubble was given by this formula, that is 40 over the radius. So obviously the pressure inside the bubble is greater than the atmospheric pressure, because always when we write the expression, so the excess pressure we write inside pressure minus outside pressure. That means the inside pressure should be high. Pressure inside should be high. So from A to B, what you have to see is, from A to B, the pressure is not the atmospheric pressure, but it is constant. Okay, it's an air region. So the value of pressure is something greater than the atmospheric pressure. Okay, atmospheric pressure plus something. So from A to B, now I'm sketching. So this is the level of atmospheric pressure. So from A to B, the pressure is something greater than that. So from A to B, it should be something like. Okay, then now we will come from C to the other. I mean, you can come from anywhere to any point, but I'll choose to come from C. Okay, now I'm again trying to draw this from C. So C, just before C, this meniscus. So at C, this meniscus is there. So just before the meniscus, it is atmospheric pressure. But just after the meniscus, what will happen? Again, you know, okay, if there is a meniscus, again there is a pressure difference that is given by 4T upon R. Sorry, 2T upon. Okay. If there is a liquid meniscus, so you can see one side of the meniscus there is the liquid. So if the liquid present in one side, the pressure difference is given by 2T over R. And obviously, by just looking at the curvature of the meniscus, okay, if you look at the curvature of the meniscus, you can easily conclude that the pressure upper to the meniscus is greater than the pressure lower, right? The lower pressure. So that is why this meniscus is arranged this way. So if it is arranged this way, the pressure from the side should be higher or greater. That means the pressure just below the meniscus should be something lower than the upper end. Upper pressure is the atmospheric pressure. උඩින් තියෙන atmospheric pressure එක. ඒතර ඊට වඩා පොඩ්ඩක් අඩු වෙන්න ඕනි පල්ලෙහාට යද්දී. That means here at the meniscus the pressure, there is a quick pressure difference, the sudden pressure drop, that is given by this equation. Okay. The pressure is dropped to some value. Then from C to D what happens? So when moving from this point to a point just above the meniscus B. So at B again there is a meniscus, and they have given that the meniscus is something like this. I mean, the shape is, the curvature is to the forward direction. So when coming from C to D, what should happen? Obviously, now when coming from C to D, the pressure will be increasing, because if you consider an intermediate point, the pressure there, let's say P dash is equal to the pressure just below, let's say it is P naught. Here the pressure, if I assume P naught, let's say P double dash, if I assume P double dash, the P double dash plus some hydrostatic pressure, right? මෙතන point එකෙන් pressure එකෙන්නේ මෙන්න මෙතන pressure එකට මෙන්න මෙතනින් යන liquid column එකේ hydrostatic pressure එක එකතු වෙලානේ. That means from C to point D, the pressure will be increasing linearly. You see, the pressure is proportional to this H. That is a linear relationship. Now this pressure should be increasing linearly. By the way, when it is approaching B, so when you compare the pressures in both sides of meniscus B, meniscus B එකේ pressure එක compare කරොත් දෙපැත්තේ, obviously by just seeing at this meniscus, by just looking at the curvature, you can conclude the pressure below is something high, and pressure below is something higher than pressure for the meniscus. Okay, that means even if it increase, it will not increase up to the, I mean, this pressure here. When you make any meniscus below pressure, what will happen is there will be another pressure drop like this. Okay. So this is the pressure drop. This is the pressure drop occurring at the meniscus B. So I can write del P2, and this is the delta P1 that is occurring at the meniscus 1, C. The graph should be something like this. So now it is sketched. Then second one, the soap bubble of radius 2.5 millimeter is formed at the lower end of the thin glass tube of internal radius 0.5 millimeter. The length of the tube is 15 centimeter. The bubble is balanced by a small liquid column of 4 millimeter, which is formed by the same liquid. Find the surface tension of the soap solution. Assume that the hemispherical menisci are formed at both surfaces. The density of soap is 1000 kg per cubic meter. මේ තියෙන meniscus දෙකම hemispherical. So if that is hemispherical meniscus, what you can, I mean, the simple thing that you can conclude is, if you consider the radius, if you consider the radius of both meniscus, let's say R1 and R2, So let's say rather RC and RB, both of them are equal to the radius of the tube. That is because it is hemispherical. Meniscus එක hemispherical නම් ඔයාලට මතක ඇති meniscus එක hemispherical නම් meniscus එකේ radius එකයි tube එකේ radius එකයි same. Same. Okay, so just write equations then. Now the heights are given. What you want to do is you have to calculate the surface tension. So let's take the surface tension as T. T කියලා ගමු surface tension. මේකේ දෙකම හදලා තියෙන්නේ soap bubble. කියන්නේ soap වල ඉන්නේ. Soap solution එකයි soap bubble එකයි. ඒතකොට මේකේ surface tension T තමයි. Okay, first I'm writing the equation for the soap bubble. Okay, let's say I'm going to take pressure here, PA. Okay, so PA minus T outside, that is the atmospheric pressure, is equal to 40 over the radius of the bubble. I'm going to take it as capital R, the radius of the bubble. This is radius of tube. R is radius of bubble. There are two other meniscus. So meniscus B, I'm writing the equation for the meniscus B. Pressure difference. So let me take the pressure here, P1, and how I have taken it from the margin. Let's do the same way. Okay, so they have just I'm gonna do the same thing like the one which is done in the marking. So let me take the pressure here just above the meniscus is PB, and the pressure just below the meniscus, upper meniscus, let's say PC. Okay, so if I write the equation for the meniscus B, in one side that is the pressure PA, PA is from the one side, that is higher as well. PA minus PB should be equal to D upon. Now the radius is simple R. You know, if it is hemispherical, the radius is the same radius of the tube. So this is the first equation, this is the second equation. And if you consider C, PB minus PC is equal to 2T over simple R again. Sorry, P naught minus PC. So when you consider the meniscus at C, one side it is P naught, the other side it is PC. P naught is higher. By the curvature, P naught is higher. Okay, so three relationships, and I can write another relationship. Now all the meniscuses are considered. So I mean, in the class when we solve these surface tension problems, they have asked you is first write equations for all the meniscuses you find. Okay, 1, 2, and the soap bubble 3. Now it is done. Then if there are any liquid columns, you have to consider the pressure balance for them. Now I'm going to do that, the pressure balance to be considered. Okay, so the pressure balance for the liquid. So when you consider the pressure balance, pressure just below the meniscus is PC, PC plus H rho G should be equal to PB. So from this one I get another equation, PB minus PC is equal to H rho G. So this is the fourth equation. So after obtaining all these relationships, then you look what can you do with them. Now it is the interesting part. Now you should be able to solve all four equations and get a value. Kind of challenging, but that's why you need the practice. Okay, so how can you do this? PB minus PC is there. So let's try again to obtain a relationship for PB minus PC. Like I have three other equations. So I'm going to try to obtain another equation for PB minus PC. Another equation for PB minus PC using these three. I can do that. How? So I'm gonna uh, subtract the second one from the third just by looking at the equation. So minus PC is there, so it should be kept like that. And there is a minus PB. So if I want to make PB plus, here it is plus, so I have to multiply with a minus sign. So minus 2. And then what you have to do? Here in the third equation, there is a P naught. So I have to subtract the P naught. Minus P naught is there. So just add. I'm adding the first one. And now we will see what will happen. Okay, so the third one, P naught minus PZ and minus P uh, A minus PB plus PA minus P naught is equal to third one 2t over simple r minus second one 2t over simple r plus 4t upon capital R. Same expression getting cancelled. Minus minus will be plus. Sorry, no, yes, minus minus will be plus. And here there is a minus PA and plus PA. So these two getting cancelled. Minus PA plus PA. Again, P naught minus P naught getting cancelled. You see, minus minus plus. So PB minus PC you get is equal to 40 over capital R. This is the fifth equation. Okay, now we have two expressions for the same thing, PB minus PC, equate them. Fourth, equate them. Fifth one is equal to the fourth one. That is 40 upon R is equal to HOG. So you have to find the surface tension. T should be equal to H rho G capital R over simple 4. Here capital R, what was capital R? I assumed capital R to be the radius of the bubble. So use the formulas, use the given data. Height of the liquid column. Height of the liquid column was given 4 millimeters. You can't substitute in millimeters, make it meters, minus 3. Density 1000, gravity 10, R. Radius of the bubble. Radius of the bubble is 2.5 millimeters. 2.5 to the power minus 3 divided by 4. 4 get cancelled, 1. Minus 3 plus 3 get cancelled. 2.5 into 10 to the power minus 2 Newton per meter. So that is the surface tension of the liquid. Okay, a good one. Then there's another part D. I'm going to continue with that one quickly. Soap bubble is formed, soap film is formed using the same soap liquid on rectangular loop of wire with one side is movable as shown in the diagram. Okay. So there is a rectangular loop like this. One side is movable, this side. So it is moving with some force, and the soap bubble is formed. Soap film is formed on this loop. Okay. Right. දැකලා තියෙනවද සබන් මේ soap වලින් අපිට උමා දාන්න පුළුවන් දැන්. Maybe you have done this. මොකක් හරි loop එකක් වගේ අරගෙන මේකේ සබන් පොඩ්ඩක් liquid එකත් එක්ක ගෑවනම් film එකක් හදාගන්න පුළුවන්. So calculate the minimum force required to hold the movable wire on the loop. Okay. So what is the force needed to hold this? So why should you apply a force to hold this? That's because the surface tension forces caused by this film. So this is a surface, a liquid surface. So the tension forces will be there. How the surface tension forces are applied? they are always applied perpendicular, right? They are always applied to the perpendicular to the line. Okay, so all the forces are to the same side. That means the resultant should be something like this. So if you want to hold this, you should apply the same force which is equal to the resultant surface tension force. How to calculate the surface tension force? You can evaluate the surface tension force, the surface tension coefficient times the length. You remember F equal TL. This a simple equation we learned in the beginning of surface tension lesson. By the way, you have to notice another thing. This is a film. This is a film. Film means, I mean, if you look at it from the side, there are two surfaces. Right? First surface and the bottom surface. This is the thickness of the film. So in both surfaces, there will be surface tension forces. So to account all of these, you have to multiply this whole equation by 2. So when there is a film, you have to do that. I mean, in both sides, if it is air, I have told this in the class. If both sides there is air and only a liquid film is in the middle, then you have to multiply equations always by 2. So 2 times the surface tension coefficient we already found the same liquid. So 2.5 10 to the power minus 2, and the length should be the length of this this wire, that is 16 centimeters, right? 16 10 to the power minus 2. So what's the value? 5 into 16 is 80. So 8 into 10 to the power minus 3 Newton. So the answer should be something like this. I think it is. Yeah. Now, last part. The force holding the rod is removed. The area of the soap bubble slowly reduces until the 20 centimeter length becomes 10 centimeter. If the mass of the rod is 40 grams, what is the velocity gained by the? It's a good question. Um, those are for the really um, the friends who have gone to the depth of this lesson. Those questions are for them. Okay, so let me go that here. Okay, so I'll do it. Just take the notes, the previous calculations we did. Take the notes. Okay, so last part, something important for all. So what they say now, what happens is its holding force is removed. This is removed. So when it is removed, what should happen? The surface tension forces will not be gone. They will be still there. So if the surface tension forces are there, under the surface tension forces, this will start some motion to this side. And what will happen? So when the motion is initiated, uh, the velocity should increase. So they are asking to calculate final velocity after some time. I mean, after this length is reduced to 10 centimeters. Initially it is 20. So after it is reduced to 10 centimeters, they are asking what is the velocity. Okay. I mean, the easiest way to do this is considering the energy. Okay. How can you consider the energy? So just identify, okay, how beautiful is this. So what is the energy conservation? So what happens is because of the surface tension forces, I mean, with the surface tension forces, when it comes to surface tension forces, the energy we talk about is the surface energy. So if there is an area, in that area there will be some surface energy stored. Obviously, this area getting reduced means it is losing some surface energy. So that surface energy should be transferred into some other form, that is the kinetic energy of this wire. See how beautiful is that. Okay? So the decrease in surface energy, decrease in surface energy is equal to increase in kinetic energy. So what is the decrease in surface energy? You can evaluate the surface energy just by this equation. Okay, surface area into the free surface energy, which is same as this free surface area is same as surface tension coefficient. We learned that in the class. Okay, so the area, what is the area? New area. I mean, what is the reduced area? So the decrease in surface energy, you have to consider the reduced area. So reduced area means this area, right? Now the final length is become 10. So the reduced area is this. That is equal to 16 into 10. By the way, this is in centimeter square. You have to make it meter square just by multiplying by 10 to the power minus 4. So that is the area. And then the surface tension coefficient. Again, remember, this is a film. Film means both sides there will be air. So if there is air, there will be two surfaces. So total area will be twice as this. Then the surface tension coefficient. Okay. Surface tension, we found the value 10, 2.5 to the power minus 2. So this should be equal to, this is the wave surface energy equal to increase in kinetic energy. So kinetic energy is equal to half. The mass is 40 grams. So you have to convert it to kilograms just by using 10 to the power minus 3 and then v square. Usually velocity was 0. So the difference is it's same. So solve this. Minus 1. Then again you can solve this like how is it? Uh, something like these two and 40. You get v squared is equal to 4 into 10 to the power minus 2. That is v is equal to 2 into the power minus 1. That is 0.2 meters per second. So this is the final velocity of the wire after this area is. Okay, so that's how you do this. So then we can move to the third part of the third essay of this paper, the final essay. No. I know. The question is from electric fields. Recently, we covered this lesson in the class. I mean, up to a certain content until capacitors we did. Capacitors thing will be done after doing the current electricity lesson for a certain amount, certain level. Okay, so part A. Define the electrostatic field intensity at a given point in an electrostatic field. Okay, so how this field intensity is defined? If you remember, the definition of the field intensity was if you keep a certain charge at a certain point, if you keep a certain charge at a certain point, the definition of field intensity was the electric force developed per unit positive charge. Okay, the electric force generated or exerted per unit positive charge, that is called the electric field intensity. So if you keep a q charge, a positive q charge, if the force is F, then per charge for q it is F, per charge the force is F for q. So that is called the field intensity. Okay, so you have to write it in words. Okay, the electric force exerted per unit positive charge is defined as electric field intensity. Okay, write an expression for the electric field intensity E of a point at r distance from q charge. Okay, so again that is very easy. This is some theory we learn in the class. So if there is a positive charge plus capital Q, and if the distance from the charge is simple r, if the field intensity at this point is E, obviously if you keep positive charge here, if you keep a unit positive charge that is 1 coulomb, that will be an opposing force. The exerted force will be an opposing force. That means the electric field intensity should be outwards from a positive charge, and the value is 1045, and we proved this 1045 epsilon capital Q over R squared. This was the formula. So here they just asked to write it, so this is enough. Then write an expression for the force acting on Q charge which is kept at point of having intensity E. Okay, so total force, if the field intensity is E, if you keep Q charge, the total force is, from the definition we can obtain it, force is equal to the charge times the field intensity. So what is the answer for this one? The total force is equal to charge times the intensity. Okay, part B. The uniform electrostatic field is created between the Earth and a thunder cloud as shown in the figure. Fine. So there is a uniform electric field. What do you mean by a uniform electric field? So a uniform electric field means an electric field, all points, the field intensity is equal. I mean, each of these points you consider, the electric field is the same thing. The value is same. Okay. The value we also mentioned in the first part. The value of the electric field intensity is 2 into the power 3 Newton per Coulomb. So the force per unit charge, charge is measured in Coulomb, Newton. So Newton per Coulomb, that's the unit. Find the resulting force acting on a ball having a mass 5 gram and charge 500 to the power minus 6 Coulomb. Okay, so we don't consider the mass. We don't need it. The force you can calculate Q times E. The charge is 500 to the power minus 6. The field 2000, 2 into the power 3 other words. So minus 3. So 1 into 10 to the power minus 2 Newton. That is its total force. Okay, second part, I am going to do the same point. Find the acceleration of the ball. Okay, so how do you evaluate the acceleration? So when you have given the mass, when you have the force, you can calculate the acceleration. How? Using Newton's second law. Just the acceleration is equal to force divided by the mass. The force is 10 to the power minus 2 and mass 5 to the power minus 3. Why minus 3? That's because it is given in grams. You have to make it kilograms. So minus 3. So 10 divided by 5, that is 2 meters per square second. So this is the whole acceleration. So all these questions you just see when we are substituting certain value, most of the time we use the SI units. Okay, I mean, even I say all the time use SI units, that's also okay, because if you use SI units, you don't get wrong results or wrong answers. Always go with the SI units. Okay, so then the third part, let me erase the other side first. Third part. Now the ball enters into an electric field under 6 meters per second horizontal velocity. Draw the path of the ball in the electromagnetic field. Okay. Oh, wait. Here there was a mistake I did for the second part. Here. This is wrong. I didn't consider the direction there. I just calculated the acceleration caused by the electric field only, by the way. So you see, this is about this field. I mean, they have clearly mentioned how this electric field is arranged. So the charge is kept here. So if you keep the charge here, obviously the electric force should be upwards. I mean, if the charge is a positive charge, if a charge is a positive charge, then the force is also acting to the same direction of the electric field. That's a theory we learned. Okay, if the electric field is to a certain direction, the force on a positive charge is to the same direction as well. By the way, that's not the only force here. Okay, so this is near ground. That means the gravitational force is also there. You have to consider that as well. Now you have to calculate the acceleration, the downward acceleration. Normally, if there was no any electric field, if this electric field is not there, then what will happen? If there is no any electric field, obviously this will be the gravitational acceleration, right? The acceleration due to gravity. Now what happens is there will be an electric force. Because of this electric force, the acceleration due to gravity is getting like kind of slowed down. Okay, kind of decreased. So if you apply F equal ma there now, downwards, the resultant force is not only mg, by the way, there's this electric force. So mg minus F is equal to the mass times acceleration. Okay, now you can find the acceleration. Acceleration should be equal. So I just divide both sides by m, then g minus Fe over m. Okay, g is 10. The electric force we evaluate 10 to the power minus 2 divided by the mass is 5 to the power minus 3. Okay, again getting the same mass. Okay, it is into meters per square second. Here, if you solve this, this is 2 again. 10 minus 2 is 8 meters per square second. Sorry, yeah. So that's the answer for the second one. Now the ball enters the electrostatic field under 6 meters per square second horizontal velocity. Draw the path of the ball in the magnetic field. Okay, so this is the area. So this is the cloud and this is the area. So the ball is entering at 6 meters per second horizontal velocity. So what should happen? Now there's no difference, by the way. Okay, only difference is the downward acceleration. The value is different. Okay, normally if there was no this cloud, the cloud is not, if the cloud was absent, then the downward acceleration is, the gravitational acceleration is, that is 10. So if that is the case, we know this will be a projectile, a horizontal projectile. By the way, in the new case also, the only difference is the magnitude of the acceleration is now less, but still it is a downward acceleration. So what should happen? If this enters the field, there will be a downward acceleration. So under that, the motion will be again a projectile. The path will be a projectile path. Okay. That will be the case. So you should have to clearly mention it, or just draw the path to be a horizontal projectile like this. Okay, that's enough. Now, fourth part, when the ball dropped from the on the earth, it has moved 30 meters horizontal distance from the starting point. So before getting before hitting the earth, before coming to contact with earth, the ball has moved 30-meter horizontal distance. So now asking, what is the vertical height? Simple, okay? Projectile motion thing. So consider the horizontal motion. So horizontally, the velocity does not change. The horizontal velocity is given. So throughout the motion, that velocity will be there. It will not change. So 30 should be equal to 6 into t. So the time taken to reach the ground should be 5 seconds. So if that is the case, if the time is 5 seconds, you can consider the vertical motion. When you write an equation for the vertical motion, you can calculate the elevation, the initial elevation. That is, h is equal to initial vertical velocity. What is the value? Initially, the velocity was horizontal. That means the vertical velocity is 0 plus half into, now the acceleration is 8 times 5 square. So the value is 4 into 21 is 100 meters. Initial height is 100 meters. Okay. I think it's all clear now. Okay, the last part and the most, I think that is the kind of the hardest part of this question. Let's see. Following figure shows a concentric conducting shell and conducting sphere. The external radius and thickness of the conducting shell is the external radius and thickness of the conducting shell is I think that is to be corrected. I think it should be 12 and 3 centimeters, right? It should be 12 and 3 centimeters. The radius of the conducting sphere is 5 centimeter. Okay. In the diagram they have given the correct place. This is 12. In a sphere, all these, I mean, both of these conducting, I mean, sphere and the shell are made of conductors. So they are working as conductors. Okay. Copy the diagram, copy the above diagram on your answer sheet and mark the induced charges on the surfaces of the sphere when plus 5 microcoulomb charge is given to the inner sphere. Now what happened is they have given a plus 5 microcoulomb charge into the inner sphere. Obviously, we know if you give some charge to a certain conductor, then the charge comes to the external surface. Do what? The charge arranges on the external surface such that the potential at all these points on this surface, on this conductor becomes equal. මේ charge එකක් දුන්නාම මේක හැම වෙලෙම surface එක arrange වෙනවා. හේතුව තමයි මේකේ තියෙන potential එක හැමතැනම equal කරනවා. හරිද? potential එක same කරන්න. potential එක same කරනවා කියන්නේ electric field එකක් ඇතුලේ නැහැ. ඒ දෙකම either way you can remember this. So when the charge is given, that will arrange on the external surface of this inner conducting sphere. So plus 5 microcoulomb. Do you remember? Now when you consider this external shell, again the same thing should be ensured. The potential inside should not change. That means the electric field will be 0 inside. Okay. So in this space, within the space of this shell, the electric field should be 0. So if the electric field is 0, what should happen? So just if you consider a Gaussian surface, inside the sphere, to make the electric field 0, what should happen? To make the electric field 0, you have to make the flux 0. To make the flux 0, if you remember by the Gaussian law, what they say is net flux is given by net charge divided by epsilon. So if you want to make the net flux 0, you have to ensure the net charge inside the surface, inside the Gaussian surface being 0. Okay. So the net charge inside the Gaussian surface should be 0. So there is a plus 5 microcoulomb charge. So to make the total charge 0, what happens is there will be the opposite charge induced in the inner surface of this conducting shell. Like this is what the conductors always do. So if there is a charge, even if there is no charge, because of the external electric fields coming affected, because of those external electric fields, they will like they will distribute their charges such that the potential affected for the shell become equal. Okay. ඒ කියන්නේ යාගේ තියෙන charges ටික කොහොම හරි distribute කරගෙන potential එක same කරගන්න එක තමයි කරන්නේ. හරිද? So what happens is if there is a plus 5 microcoulomb charge, there will be the minus 5 microcoulomb charge induced in the inner surface. Then minus 5 එක induce වන ගමන් මොකද්ද වෙන්නේ? දැන් ඇතුලේදී net charge එකක් නැහැනේ. ඒතර electric field එක 0 වෙලා යනවා. By the way, now there is a problem. So the conductor itself induces a minus 5 microcoulomb charge on its inner surface. By the way, the net charge of this conducting shell should be 0 because no charge was given to the external conducting shell. So if no charge is given to the external conducting shell, then the total charge should remain 0. So how that happens? How to keep that total charge still become 0? That's done by, so when minus 5 coulomb charge is induced in the inner surface, to balance it, there will be the opposite charge again induced in the outer surface. By the charge induced in the outer surface, there will be no any affection for the electric field. Okay, just by constructing the Gaussian field, you can come to that conclusion. The electric field is only affected by the inner charges. So no influence from the outer charges. So to neutralize the whole charge, the opposite charge is made in the outer surface. මම පොඩ්ඩක් සිංහලෙන් කියන්නම්. plus 5 microcoulomb එක ඇතුළේ ගෙනල්ලා දුන්නාම ඒක යාගේ surface එකට එනවා. Then ඒක එන්නේ conducting shell එකක් හින්දානේ. ඊට මේ තියෙන external shell එකත් conducting shell එකක්නේ. conductor කිව්වම ඇතුලේ electric field එකක් තියෙන්න බෑ. conductor එකේ sphere එකේ electric field එකක් තියෙන්න බෑ. එහෙම තියෙන්න බැරි නම් අපි Gaussian surface එක consider කරොත් මුලින් මේ +5 microcoulomb විතරයි තියෙන්නේ. ඒතර net flux එකක් තියෙනවා. මොකද flux එක දෙන්නේ charge එක බෙදන්න ඕනේ epsilon වලට. එහෙනම් මොකද කරන්න ඕනේ දැන්? electric field එක 0 කරන්න නම් flux එක 0 කරන්න ඕනේ. flux එක 0 කරන්න නම් net charge එක 0 කරන්න. charge එක 0 කරනකොට මොකද කරන්න වෙන්නේ? ඇතුලේ තියෙන charge එකට opposite charge එකක් මේක inner surface එකේ induce කරගන්න වෙනවා. -5 microcoulomb. දැන් ඒක induce කරගත්ත කියලා conducting shell එකට net charge එකක් තිබ්බ නෑනේ. ඒ මේ conducting shell එකට කවුරු charge එකක් දුන්නේ නෑනේ. -5 coulomb එක ඇතුලේ හැදෙද්දි ඒ කියන්නේ තිබ්බ total charge එක අර total value 0 තියාගන්න ඒකට opposite charge එකකින් external surface එකේ that is what is happening. Okay, so now the charges are drawn. So this you have drawn this clearly on your answer sheet. So if you have drawn it, you will get the full mark. Second part, find the electrostatic field intensities at point P, Q, R, S, and T when OP and all these values are given. Okay. P, Q, R, S, T points are also marked. Okay, so how to calculate the electric field? This thing with the Gaussian. So I'll remind you the Gaussian law. If there is a certain charge distribution, if you construct the Gaussian surface, you can first evaluate the net flux. So we are divided by the epsilon, permittivity of the medium. Then the electric field is the flux density. Okay, the total flux divided by the total area. Area means the area of this Gaussian surface. I mean, when you are choosing the Gaussian surface, when you are choosing a Gaussian surface to calculate the electric field, you should ensure that all these flux lines going perpendicular to the surface. You should ensure that all these flux lines should be perpendicular to the surface. Okay, so think with that. Just Q divided by. So this is O. The point P is something like this. Q is here. R is here. Then the shell comes. So inside the shell, the point is S is there, and T is something outside. Okay. Obviously, if you consider point O, this is inside the conducting shell. So you don't have to worry. All these charges getting induced or arranged such that the electric field becomes 0 inside the conductor. So obviously, EO and EP should be 0. You don't have to, think a bit about that. Should be 0. Q is the electric field on this, on the surface of this sphere. So on the surface there will be an electric field that is given by, so if you consider the surface, if you draw a Gaussian surface, this charge on this surface is included. So still the formula will not change, like you can apply the same formula used for the point charge, this Q over R square. So now the charge is the charge on the surface. So 1/4 epsilon times charge on the surface divided by the radius, inner radius, let's say R1. So 9 into the power 9 into the charge is +5 micro කියන්නේ -6 එකක් තියෙන්න ඕනේ divided by the radius, the OQ distance they have given 5 to the power -2 square. So you just solve this and see what is the answer. I'm not going to solve this, and I think 4.4 something 4.5 එක මොකක් හරි එකක් එන්න ඕනේ. නැද්ද? Yeah. 4.7. What is the answer? 2.25 or something. මේකෙන් ඕනේ. Just see after you solve it. Okay, so that is the value for EQ. Then ER, again, when you calculate for ER, again consider a Gaussian surface from that. So if you consider a Gaussian surface which is passing through point R, again it should be spherical so that all the flux lines are moving perpendicular. So the charge inside is only this charge on the surface. Okay. So again you can apply the same formula. So that charge is in, so 1/4 epsilon Q over, let's say R square. So 9 to the power 9. The charge included is 5 to the power minus 6 divided by, what is your OR? OR is 8 into 10 to the power minus 2 square, like this. So when you do this, again you will obtain some value. So if you solve this, it should be something like this: 7.03 into 10 to the power 6 Newton per coulomb. So I just want you to show you the logic behind. I mean, how obtaining these expressions, right? So the first, inside conductor, there is no any electric field, 0. Then Q and R, how I got to the answer was just by using the Gaussian surface. I just think of a Gaussian surface and evaluated the net charge. So once we evaluate the net charge, if you remember, for circular sections, still this expression is valid. Circular center, like we learned this formula in the class. I mean, for any, spherical or any shell kind of thing, this equation is still valid, but only when you consider a point which lies outside. Okay. කියන්නේ මේක කියන්නේ ස්ෆියර් එකකින් එළියට පොයින්ට් එකක් ගත්තාම ඒකට තාමත් මේ අර පොයින්ට් charge එක equation එක දාන්න පුළුවන්. So that is what I applied here. Okay. For both Q and R, they lies outside the sphere, so you can apply it. Okay. For S, again you don't consider S. You don't have to actually. Why? Because charges on these surfaces are arranged to make the electric field inside the conductor 0. Make it minus 5 mark coulomb tippane, make it plus 5 mark coulomb tippane. So these things get arranged to make the electric field here 0. I mean, if you want, you can verify it. How to verify it? Just think of an Gaussian surface going through that point. Gaussian surface එකක් ගත්තම මොකද වෙන්නේ? So if you consider the net charge inside, what is the net charge? Here there is a plus q and here there is a minus q. So the net charge becomes 0. If the net charge is 0, then the electric field should be 0. Obviously, E is equal 0. Then T. Okay, now again consider the Gaussian surface to T. So T is lying outside to both all these spheres and chairs. So the net charge is what? Plus 5 and minus 5, 1 get cancelled, but there is another plus 5. So 1/4 epsilon Q over RT squared. 90 to the power 9. Charge 500 to the power minus 6. The distance to point T is 15. 15 to the power minus 2 square. So when you solve this, I think you will get something like 2.3 into 10 to the power. It is given as 15. In the marking, they have taken it as 14. We think there's a mistake in the marking. So this should be 15. So if it is 15, then you can just have to cancel these values and go for an answer. We think the answer should be something like this: 2 into the power 16 Newton per coulomb. That should be the answer. Okay. Yeah. Then Split the variation of electric field intensity with distance from the center. Okay, just ask to split the variation of electric field with the distance. So let me mark these points. O, P, Q. Q is here. Then R in the middle. And the surface point is there. I mean, let's say this is the point at which the inner surface starts. Inner surface. Okay. And then point S comes, it is S. And the outer surface comes. And the point is there. Okay, so obviously when we draw in this, until Q, electric field should be 0 because that is inside the conductor, inside the conducting shell, conducting sphere. And again, from the inner surface to the outer surface of the shell, electric field should be 0. So those two regions, the electric field should be 0. So there is a variation only in between them. Again, you know, until this formula is valid, the electric field is proportional to 1 over r squared. So the variation should be something like this. 1 over r squared curves we learned in the class should be something like this. And these vertical lines also you should have drawn it like this. And then the same variation is followed just after this point as well. 1 over r squared. So if you have drawn this shape correctly, then you should have obtained all the marks. Okay, you will be given it all the marks. Okay, so this is the proper variation. Last one. Calculate the electric potential of P, Q, R, S, and T. Okay. So here is. So if you have questions, again raise them in the chat. I mean, none of these people have any question. Like how intelligent they are. So maybe they are just putting this as a show and just sleeping. Is it the case? Yeah, දාලා නිදිද කටිය නෑනේ. So the last one, calculate the electric potential of P, Q, R, S and T. Oh, I did the wrong. That will be coming to it. Okay, so let's see. Then I have to draw this 5 and then O, P, Q, R, S and T. So how these charges were arranged? So charges were arranged plus 5 microcoulomb was there, minus coulomb was there, and again the plus was on the outer surface. Okay. So electric potential. Okay. Let me remind you how you have to work with these problems. So let's say there's a conducting sphere like this. I'm just reminding the theory, okay? This is a conducting sphere. Let's say you have given certain charge, that charge Q. Then you are considering a certain point. First case, you are considering a point which lies outside the surface. Okay. The surface radius r කියලා ගත්තොත් radius එකට එළියෙන් තියෙන point එකක් ගත්තා කියලා. Then evaluating the potential. The potential caused by this charge distribution, the potential එක ගැන හෙව්වොත්, you just have to think this charge is kept as a point charge at the center and obtain the formula. So you can use the same formula for the point charges. කියන්නේ එළිය තියෙන point එකක් ගත්තොත් එළිය තියෙන point එකක potential එක හොයනකොට පාර කරන් තියෙන්නේ මේ charge එක ඔයා assume කරන්න ඕනේ center එකේ තියෙනවා. මේ charge එක center එකේ තිබ්බනම් මෙන්න මේ distance එකනේ consider කරන්න ඕනේ. ඒක දාලා potential එක හොයනවා. 1045 epsilon q bar කියලා කියන්නේ electric potential එක හොයන්න තියෙන formula එක. Then if the point is lying inside this sphere, මේ වගේ point එකක් ගන්න. Remember the potential is equal to the potential at the surface. Conducting sphere එකක් නේ. Conducting sphere එකක් වුණාම charges මේ විදිහට arrange වෙන්නේ. ඔව් මෙහෙම charges distribution එකක් එන්නේ potential එක same තියාගන්න. හරිද? charge distribution එකේ ඉඳලා surface එකේදී මොකක් හරි potential එකක් එනවද? ඒ potential එකම තමයි ඇතුලේ කට්ටියටත් දැනෙන්නේ. So the same potential. So for inside points, for inner points, the potential is equal to the same potential on the surface, that is equal to q over the distance to the surface. Surface එකට තියෙන distance එක consider කරන්න. Surface එකේ potential එක. Okay. ඕක තමයි කියන්න තියෙන්නේ. හරිද? ඕක ඊට පස්සේ just remember if there are like a set of charge distributions, charge distribution, then the total potential at a certain point is given by the sum of different potentials. total potential දෙන්නේ the potentials වල sum එකෙන්. Okay, so the same thing to be used here. So I'm considering point O. O කියන point එක මුලින්ම ගන්න. බලන්න මේ charge distribution තුනම එළියෙන්නේ තියෙන්නේ. All these three charge distributions are outside compared to this point O. I mean, if you consider the other way, compared to all three distributions, හරිද? දැන් මේ තියෙන charge distributions තුනටම relative ගත්තාම O කියන point එක ඇතුළේනේ තියෙන්නේ. O කියන point එක ඇතුළෙන් තියෙනවා කියලා කියන්නේ තුනේම surface එකේ තියෙන potential එක තමයි මෙතන දැනෙන්නේ. O කියන point එකට දැනෙන්නේ තුනෙන්ම surface එකේ තියෙන potential එක. So 1045 epsilon plus 5 in 10 to the power minus 6. මුලින්ම ගන්න මෙයා. ඒතර එතන surface එකට තියෙන distance එක වෙන්නේ distance is given, right? It's 5. This centimeter. I'm not going to solve this. Again, by the minus 5. So there is a minus 5 coulomb here, microcoulomb. So that by that one, again the distance to the surface is 9 centimeters, right? Minus 2 to make it to meters, centimeters, given values. Again, to the outer surface, 5 to the power minus 6. To the surface, the distance is 2. You have to solve this. Make a circle from a step back one and then make it back only. 1045 epsilon can 9 to the power 9. Take a given. Question they have mentioned it clearly here. You see, here they have given that. So again, you can take 5 to the power minus 6 out of the equation, and again minus 2 as well comes down. 105 minus 109 is 112. So you have to solve this and obtain the answer. I'm not going to solve. Compared to P, P also the same thing, isn't it? Compared to P, all these surfaces are outside. So it is the other way. Point P lies inner to all three shells, all three charge distributions. So the surface potential is there. What else you think of point in this way also? So both these points are inside the conductor. So we know the charges arranged to make the potential equal. Conductors will charge arrange potential same tiyaganane. So Vp should equal to V0 or Vo. That is the answer you obtained in the previous case. Again, no difference. Again, if you consider Q as well, Q also the same conductor. So Vq also should be equal to Vp. That is equal to V1. Again, that is also solved. Then comes to R. R is something different. R is something different. When you come to R, okay, when you consider point R, R is outside compared to this inner charge distribution. මෙයාට comparatively මෙයා එළියෙන් තියෙන. But for other two, it is inside. Okay, so when it is outside, you have to consider the distance to that point නේ. එතන දැන් මේ කිව්වේ එළිය point එකට සාපේක්ෂව එතන distance එක ගන්න ඕනේ. And the total potential මේකේ charge distribution තුනක් තියෙනවා. තුනෙන්ම එන result එක වෙනම එකතු කරලා ගන්න පුළුවන් මේ. තුනෙන්ම result එක මෙහෙම ගන්න පුළුවන් වෙනවා. So 1/4 epsilon common හින්දා මම ඒක මුලින්ම ලියා ගන්නවා. So the result by this inner charge. So when you consider the inner charge, you have to consider the distance to the point. So what is the distance over? 8 centimeter. 8 to the 10 to the power minus 2 plus, sorry, minus, there's a minus charge there. Minus 1 to the power minus 6 divided by, so මේ දෙන්නම එළියෙන් තියෙනවා. Surface area distance සුරකාරම් හරි. Surface එක minus මේක යාර. එක 9 cm අනිත් එකේ then you have to solve this. Okay, I'm not going to solve this. Again, you can take this 5 into minus 6 out as well as minus 2 from the downward as well. Okay? Minus 2 you have to. So VR is also done. Then Vs. Vs is the potential inside the conducting shell. Okay, so compared to point S, what should happen? So compared to point S, compared to the Gaussian surface drawn through point, two charge distributions are inside. දෙකක් ඇතුලෙන් තියෙනවානේ. මේ දෙකේම ඔයාලට කන්සිඩර් කරන්න පුළුවන් මේ දෙන්නම සෙන්ටර් එකේ තියෙනවා කියලා. ඒ කියන්නේ මම කිව්වේ දැන් මේ එළිය තියෙන පොයින්ට් එකක් ගන්නකොට මේ තියෙන charge එක ඔයාලට සෙන්ටර් එකේ තියෙනවා කියලා හිතන්න පුළුවන්. ඒත් මේ දෙන්නම එකට හිතන්න. lazy. So if you consider both of these charge distributions at the same time, then what will happen? This is going to the center. This is also going to the center. Plus 5 microcoulomb, minus 5 microcoulomb getting cancelled at the center. So no charge inside. So no potential from the inside. By the way, there will be some potential developed from the outside charge. That is the potential on the surface, that is 500 minus 6 divided by the distance to the surface is 12. ඉෂ්ඨ කම්පරට්ලි ගත්තාම මේක එළියනේ තියෙන්නේ. රෙලි සර්ෆස් එකෙන් කන්සිඩර් කරනකොට සර්ෆස් එක එළිය නම් තියෙන්නේ මේ වගේ පොයින්ට් එකක් ගන්නකොට සර්ෆස් එකේ වැලියු දාන්න. يعني සර්ෆස් එකට තියෙන රේඩියස් දානවා. 12. Again you have to solve this. I'm not going to solve. Then T. So compare point T to these three charges. You can consider they are at the center. And compared to point T, all three charge distributions lies inside. All three charge distributions lies inside. So 2 get cancelled, but 1 will be remaining. You have to consider the whole distance to the point T. That's the point. Previously, you considered the distance to the surface, but now T is outside. So 1 plus microcoulomb is there. So the total distance to point T should be considered as 15. Okay, so again solve this, you will get the correct answer. Okay, so that's how you calculate the electric potentials. So again, recall these theories, okay, how you calculate the electric potentials in this kind of charge distributions. If there are multiple charge distributions, you have to know how to evaluate the potential. And these type of questions are more frequent in the previous papers. So you should be able to solve something like this. We don't know whether what is the question you get in your exam. It can be either like when it comes to fields, there will be one question from all three fields lessons: the gravitational field, electric field, magnetic field. We don't know what field will be asked in the certain year. By the way, the last year it was gravitational field, I think. So this year, mostly, I don't know whether this will be 100% sure or not, but mostly it will be either electric field or magnetic field. Okay, maybe both of them. So when it comes to electric field and magnetic field, sometimes they can give like combined questions. Okay, so so keep that in mind. Okay? So that's how you do it. Then now we can finish the class, right? Now the time has come. So for the rest of the paper, then you have the marking. Again, I didn't find any problems with the paper. So if you find anything like unsure, the answer which is mentioned in the marking, if you find it is unsure, then directly contact me. Okay, all these things we have discussed in the class, the theories. So what I want you to is to follow with this process. Take time, it will take time, but with time you will get, what you didn't expect, you will be. It is the simple scenario. Okay? Time can do a lot change. Like, so these days the time also like a very important factor, because with the time we don't, very big processes are going on in this world right now. So that's how this time is important. We don't know what is time actually is. Why don't we have something like that? Okay, so hope you don't have any questions. Again, if you have any questions, please raise them now, or else you can directly ask me. And again, I have to mention this. So most of the time in the class, what I do is I discuss MCQs and essays, okay? Because my main focus these days is to just, I want you to recall all the theories what you have learned up to now, as well as the certain lessons which are more important to your final physics paper. Okay, so those lessons are more frequently questioned in these revision papers. So get ahead with these revision papers, follow all the MCQ questions, do the essay questions, and get that knowledge. Okay, update those knowledge. So once you're done with this revision paper series, it will make sure that you will like go through most of the content you find that is important for the final paper. Okay, so I'm mentioned 100%. By the way, most of it will be covered. So after completing this, like we will be able to cover the. I mean, we will complete the revision paper series. I think end of this month or maybe 2 weeks of the next month. Okay. So at that point onwards, we will be starting I think full papers. So until that, keep revising through the lessons. Okay. Uh, that is the whole point we having doing this weekly. And don't worry about the structured essay questions for now. Again, go through the the video lessons I have provided, so that will make you like all the points you require to the practicals. Then I mean, at the end of each lesson, I'll provide you with the practical questions which have asked in the previous lessons as well. Okay, the past papers booklet I give you all the theory people. So you have all the material if you want to go through the practicals in the same manner. But I think it will be more efficient if I discuss the practicals later when it is more closer to the exam. So then you will, I mean, most of you may have the work mindset, so it will be easier to deal with those practicals. That's fine. Okay, so see you in the next session that we will take. So until that, goodbye everyone. Okay. Goodbye.